Good day, and welcome to the New England's Biolabs, Inc. Elucidating the Complexity of Heparin Oligosaccharides Analyst Conference Call. Today's conference is being recorded. At this time, I'd like to turn the conference over to Alicia Bielig. Please go ahead, ma'am.
Hi, thank you everyone for joining us today as we discuss the elucidation of the complexity of heparin oligosaccharides. I'd like to start with a brief introduction about heparin and heparan sulfate. They are glycosaminoglycans, which are long, linear, sulfated polysaccharides. They're located on cell surface membranes and in extracellular matrices. As you can see on the figure on the left, they begin with a tetrasaccharide linker, which is attached to a serine residue on proteins. From there, chain polymerization occurs, which creates repeating disaccharide units. These repeating disaccharide units consist of a glucuronic acid with a beta-1,4 linkage to an N-acetylgalactosamine. They're polydispersed with respect to sulfation and acetylation in uronic acid epimerization. As you can see the figure on the right, this is the repeating disaccharide unit in which the R, the X, and the Y groups can be modified with either a sulfate, an acetyl group, or a hydrogen, making them extremely diverse and complex. The structural complexity of heparin and heparan sulfate may be challenging. However, researching its range of biological functions is important to the field of glycobiology. This is due to the fact that heparan sulfate chains can bind to a variety of different proteins, as you can see in the chart below, including a variety of growth factors, chemokines, extracellular matrix proteins, and enzymes. In addition, heparin is widely used as an anticoagulant drug. It's been shown to regulate cellular processes by binding, stabilizing, and activating various growth factors. The complexity of heparin and heparan sulfate is often due to the biosynthesis because it does not follow an exact template and many steps fail to go to completion. As you can see in the figure shown here, it starts with a tetrasaccharide linker. Chain polymerization occurs by several transferases. From there, steps occur with enzyme modifications to deacetylate, to epimerize glucuronic acid to iduronic acid, and to place sulfate groups along the chain. However, because many of these fail to go to completion, polysaccharides are created with alternating N-acetyl domains with low sulfation and N-sulfated domains with high sulfation and epimerization. These different domains make these long heparin-heparan sulfate chains very diverse and very complex. Therefore, in order to elucidate these complex polysaccharides, it's an extremely challenging task, and it's one that can't be accomplished without creating oligosaccharide intermediates using tools such as heparin lyase enzymes. Currently, there's 3 heparinase enzymes commercially available. Heparinase 1, which acts primarily on highly sulfated heparin and heparan sulfate chains. Heparinase 2, which acts on both high and low sulfated domains. And heparinase 3, which acts exclusively on less sulfated chains. If you look at the mechanism shown on this slide, you can see the action of the heparin enzyme in which the heparinases cleave the glycosidic linkage between hexosamines and uronic acids via an elimination mechanism. This elimination mechanism creates a double bond on the non-reducing end of the uronic acid that absorbs at 232 nanometers. Because it can absorb at 232 nanometers, this digestion can be observed in real time, allowing you to follow and decide if you would like to do a partial or a complete digestion. In order to show how one can use these enzymes in order to elucidate the complexity of these polysaccharides, we'll show the creation of a hexasaccharide. So to create a heparin oligosaccharide, in this case, we'll be showing you how to create a heparin hexasaccharide. We can treat 1 ml of a 3 mg per ml heparin solution isolated from a proteoglycan source with 0.5 to 25 microliters of Bacteroides heparinase 1 in heparinase reaction buffer for 4 to 56 hours at 30 degrees. You can read the absorbance values in real time at 232 nanometers every 4 to 8 hours to determine when the reaction is complete. This reaction can be scaled up or down linearly. However, we're showing you on a semi-preparative scale. So for a given substrate and enzyme concentration, the time to produce a partial digest or a complete digest can be precisely controlled. This can be controlled by following the digestion at 232 nanometers as shown in the graph to the left. Complete digestion can be determined by no change in OD at 232 nanometers. So as you can see in the figure to the left, as the line starts to plateau, the OD is not increasing. If you add additional heparinase enzyme and you do not see further increase in OD at 232, you can know that your reaction has gone to completion. It should also be noted if you're doing this on a semi-preparative or preparative scale, you're most likely going to be using enough heparin or heparan sulfate that it will go off scale and it will require 1 to 100 or 1 to 1,000 dilution of the enzyme in order to read. In addition to monitoring at 232 nanometers, you can also monitor the extent of a heparinase digestion using LCMS. In this case, we took 1 microliter aliquots of our digested heparin solution. We diluted it in 200 microliters of a 90% acetonitrile and 10% ammonium formate buffer, and we loaded it onto a hillock column. And our choice is an amide column, and we monitored the extent of digestion. The oligosaccharides are eluted following a 30-minute gradient, starting at high organic, 90% acetonitrile, and ending at a lower organic, 40% acetonitrile, and a higher aqueous, 60% ammonium formate. As you can see on the chromatogram to the left, the disaccharide peak is the largest peak because it was a complete digestion to 56 hours. And then we have our tetrasaccharide and our hexasaccharide peaks eluting later. The retention time increases as the size of the oligosaccharides increase when using hillock chromatography. And for oligosaccharides of the same size, retention times increase with higher sulfate content. So this is a good way to footprint your protocol in addition to real-time UV at 232. So following a digestion, if you'd like to isolate an oligosaccharide, in this case we're going to isolate a hexasaccharide of interest, you can isolate that by loading and eluting the digested heparin solution through a size exclusion column equilibrated with 0.2 molar ammonium acetate. In our case, we're using a P4 biogel size exclusion column. We're interested in the hexasaccharide. So we can see here that the hexasaccharide peak elutes prior to the tetrasaccharide and disaccharide peak. We know the mass of our hexasaccharide of interest, so we can take a fraction from this peak. We can analyze it by mass spec to see if we have that peak of interest. We know our mass, and the mass to charge ratio for the triply charged ion is 536. We see that in our mass spec analysis. This is not a pure hexasaccharide at this point, so we also see many other peaks and noise peaks present, telling us that we need to further isolate the oligosaccharide. It should also be noted that in order to optimize the chromatographic separation of these oligosaccharides, you can determine specific biogel P-size columns. We'd recommend a P2 column for a dimer or a tetramer. We recommend a P4 column if you're looking to isolate a tetramer or hexamer, and we recommend a P10 column for any oligosaccharides of hexamer size or larger. So to further isolate the oligosaccharide, you should lyophilize your SEC pool and reconstitute in 2 mL of a 0.1 molar ammonium formate at pH 3.5. You can then load this reconstituted pool onto an equilibrated ion exchange column and elute the oligosaccharides with a 20-column volume linear gradient ending in 1 molar sodium chloride and 0.1 molar ammonium formate. In our case, we've used a source TM15Q column. We're interested in our hexasaccharide, which we know will elute after our largest peak, which is the disaccharide. We can desalt this hexasaccharide peak to remove the sodium chloride, and we can analyze it by mass spec to confirm that this is our mass of interest. So if you look at the mass spec, you can now see the doubly charged, triply charged, and quadruply charged ions of the hexasaccharide of interest. We also see adduction of these charges due to the fact that we're spraying an ammonium formate buffer. In addition, there's also some noise peaks due to the fact that this is not a completely pure product jet. We can take this hexasaccharide pool from the ion exchange column, and we can isolate it further by pooling it, lyophilizing it, and desalting using a G25 column. We then take the desalted pool and we reconstitute in 1 to 2 mL of an 85% acetonitrile and 15% ammonium formate buffer. We can then equilibrate a hillock column. Again, we've chosen an amide column with 5 column volumes of 85% acetonitrile and 15% ammonium formate. We then load our sample onto the amide column and elute the oligosaccharides with a 4 column volume gradient, starting at 85% acetonitrile and ending at the reverse, 85% ammonium formate. So when you see the amide column profile, you can now see that we have one pure peak, which represents our hexasaccharide of interest. If we take a fraction of this peak and spray on an ion trap mass spec, we can now see our major peak with a 4- ion at 402, and we have a triply charged ion at 536. You see the absence of many noise peaks showing that we have isolated our hexasaccharide of interest. So during and following the isolation and purification of heparin and heparan sulfate oligosaccharides, the most common method of downstream analysis is mass spectrometry. Electrospray ionization has proven the most effective for the MS analysis of sulfated carbohydrates, such as heparin and heparan sulfate. And although these oligosaccharides can be difficult to analyze by MS without using finely tuned ESI parameters to reduce or eliminate in-source fragmentation of sulfated oligosaccharides. Highly sulfated heparin oligosaccharides with defined structure, such as the hexasaccharide that we've just shown how to isolate here, can be used to optimize these tuning parameters in various mass spectrometers. The figure here shows the hexasaccharide that we've just isolated with the structure and its exact mass, including its mass to charge ratios in order to watch by mass spec. So if we take this isolated heparin hexasaccharide, which has 7 sulfates, and we analyze it on an ion trap mass spectrometer that's been equipped with a heated electrospray standard source running in the negative ion mode without prior tuning, the resulting spectrum is shown here. And what you see is the M4 ion at 402, which is your ion of interest. And then you see a loss of sulfate at 382, a second loss of sulfate at 362, a third loss of sulfate at 342, and a fourth loss of sulfate at 322. You can also see loss of sulfate of the 3- ion at 510. So incorrect tuning parameters leads to in-source fragmentation and sulfate loss. And the more sulfate groups that are present on an oligosaccharide, the greater the sulfate loss will be in ESI. Due to this fact, it is extremely important to have the correct tuning parameters for sulfate stability. Every single mass spectrometer will have variable tuning parameters. Some of the most important tuning parameters are the capillary temperature, the S-lens, the skimmer, and the spray voltage. And these are all crucial settings for reduction of in-source fragmentation. The recommended ion trap mass spec parameters for the ion trap used in this presentation include all of the parameters shown below, and I'd like to highlight the 3 that were of most importance: the spray voltage, which was 3.5 kilovolts, the capillary temperature, which was 250 degrees Celsius, which I would note is typically lower for heparin sulfated oligosaccharides than it is for other molecules. And in the case of this ion trap, an S-lens, which had a level of 14. This is also similar to a skimmer. Many mass spectrometers have different ion optic settings that need to be looked at on a case-by-case basis. So if you take that same isolated heparin hexasaccharide with 7 sulfates and you analyze it on the same ion trap mass spectrometer equipped with a heated electrospray standard source run in the negative ion mode with the recommended tuning parameters, the resultant spectrum is shown here. You see the 4- ion at 402, which is the primary ion in the spectra, and you only see 1 loss of sulfate at 382, and it takes up less than 10% of the spectra. So the sulfate loss with correct tuning parameters is reduced to less than 10%. It's also good to note that in ESI, sulfate groups are most abundant in their ionized form. Therefore, as the instrument is tuned to avoid sulfate loss, it will be less likely for the low charge states to appear, which is one of the major reasons you see primarily the 4- ion and the 3- ion with the absence of the 2 and the 1- ions. It can also be shown, if you look at the prior to tuning, that you had over 50% sulfate loss as compared to after tuning when you've reduced to less than 10%. Different mass spectrometers will require different tuning parameters for the analysis of sulfated oligosaccharides. And charge state intensities and mass accuracy will differ between instruments. So if we take the same heparin hexasaccharide with 7 sulfates and we analyze it by time of flight mass spectrometer, you will again see the 4- ion at 402 and the 3- ion at 536. However, the spectrums will look different. In this case, we see slightly more reduction, and we see 1 loss of sulfate at 382. The recommended parameters will change for a TOF mass spectrometer as compared to an ion trap or a quadrupole or so forth. The spray voltage is 1.9 kilovolts. The capillary temperature is slightly higher at 320 degrees Celsius, and in this case we have a skimmer instead of an S-lens. So it should just be noted that you will get varying parameters and varying mass spectrometers. It's also possible when working with heparin and heparan sulfate oligosaccharides to get rearrangement of high charge states. High charge states can lead to hydrogen shift rearrangement, resulting in the loss of the double bond with the addition of two hydrogens. If you look at the mechanism at the bottom of the slide, you can see that the double bond takes on two hydrogen molecules, changing the overall mass to charge ratio of the ion. The design of the ESI probe can affect the stability of the analyte. Although rearrangements are typically observed in high-energy CID, high-charge states are susceptible to rearrangement in ESI, which is considered to be a low-energy ionization event. The sulfates on these oligosaccharides tend to lean towards high-charge states, which is why in the ion trap mass spectrometer we see a 4- peak at 402.73, even though the theoretical should be 402.24. However, after hydrogen shift rearrangement, the theoretical mass to charge would be 402.74, showing that this is a hydrogen charge rearrangement. To prove that this isn't just mass calibration of the instrument or an incorrect mass of the hexasaccharide itself, if we spray the exact same heparin hexasaccharide sulfate with hexasaccharide onto a time of flight mass spectrometer, hydrogen shift rearrangement does not occur. The theoretical mass is 402.24, and the 4- ion on the top is exactly 402.24, showing that in the ion trap it truly is hydrogen charge state rearrangement. Additional MS optimization parameters that should be noted is that the stability of the analyte is directly affected by the flow rate at any given concentration. So for LCMS with the standard electric spray source, a column splitter may be necessary to match the conditions used to tune the instrument. In addition, the significance of pH and solvent chemistry in ESI, the chemistry of the solvent directly affects the ionization abundance and the formation of ion adducts. If you spray your oligosaccharides in ammonium formate versus ammonium bicarbonate or ammonium acetate, you will see different adduction in different abundances. In addition, for a given mass spectrometer, isotopic resolution of sulfated oligosaccharides may require increased scan rates. And lastly, since sulfate loss is higher in oligosaccharides with greater sulfation, the best tuning parameters for tandem mass spectrometry analysis can only be achieved with highly sulfated oligosaccharide standards. We would recommend using a pentamer or larger. Using a highly sulfated oligosaccharide standard will work much better than a disaccharide with only 1 to 3 sulfate residues. So in conclusion, better elucidation of heparin and heparan sulfate can only be accomplished by creating oligosaccharide intermediates with a diverse set of tools such as heparin lyase enzymes. NEB now offers 3 highly characterized heparinases with unique specificities. Mass spectrometry analysis is often required for the elucidation of these heparin and heparan sulfate oligosaccharides. Successful tuning parameters must be achieved to analyze the oligosaccharides. NEB also now offers 2 highly sulfated heparin hexasaccharide standards of defined sequence and structure. To show you these products, we have heparinase 1, 2, and 3 from Bacteroides, and we also can offer now a heparin hexasaccharide MS standard 6, which is 6 sulfated, and a heparin hexasaccharide MS standard 7, which is a hexasaccharide standard with 7 sulfates, and is the standard that's been shown throughout this presentation today. So I'd like to say thank you for attending today, and for more information on the products used in this presentation or the full line of glycobiology reagents that NEB has to offer, please visit nebglycosidase.com. And now we're going to answer any questions that you might have.
Thank you. If you'd like to ask a question, please signal by pressing the star key followed by the digit 1 on your telephone keypad. To ask a question on the web, click in the Ask a Question box located on the left side of your screen. Type in your question and hit Submit. there are no phone questions.
There's a 5-second delay.
Again, there are no questions on the phone line. I'd like to turn the call back to our speakers.
If no one has any questions, then we'd like to just say thank you for attending, and feel free to visit NEB Technical Support to submit any questions at a later time, and we'd be happy to get back to you then.
And that concludes today's conference. Thank you for your participation.
Oh, there's questions in the QA tab. Where's the QA tab? I can't, but when people have signed off. There's no scroll. I don't know how to use them. How do I use them? This.
You may proceed with your questions.
The first question I have here is, have you tried other types of hillock columns? The answer would be is that we have only tried the Amide 80, but we've tried several brands, and they all seem to work pretty well. Second question is, do heparinases work on mammalian cells? Yes.
And once again, if you'd like to ask a question on the web, click in the Ask a Question box located on the left side of the screen. Type in your question and hit Submit.
There doesn't seem to be any questions at this time.
That concludes today's conference. Thank you for your participation.
Thank you.